Okay, so let's see what this assignment is asking us to do. So the current version of our program, this prototype, displays the structure of the abstract syntax tree as we already observed, and here we try to interpret the result of what gets printed. Instead of printing, we want to change the program to actually evaluate, compute the expression, and show the result to the user. So we also need to add support for the remainder operator and also add support for variables and the assignment of these variables. We have some instructions below. So here's some helpful ideas. So remember that what we're dealing with here, if you look at the main method right here, by the time we need to do our things, essentially evaluate the expression, the lexer is already completely out of the picture. We run the start rule, which right here will construct for us a tree. Right, so here the tree is already constructed, and all we need to do here is completely work, just work with the tree. Everything else is irrelevant. The tokens are already processed, all the grammar rules already were applied. Everything is out of the picture. What's left here is just take the structure and make a computation by using what we have over here. And so these are the ideas how we can do this. Alright, so we have this result. This is our root node, and we check for error. If it's an error, we just print what the error message is, and error is already generated by the lexer. So this is the parsing, the compile time error that we're printing over here. Everything looks to be okay with our syntax tree. So right now the result, which is the instance of AstNode, and what we do with it is that we print the tree. Basically, we print the underlying tree. So what this AstNode does, this is the print method here. So it just basically looks at what level of printing has been requested. So here, for instance, it starts with level 0, so it prints no periods. But if the level is non-zero, it will print 1 period or 3 periods or however how many periods you need. And then it has two parts. It has the left node and it has the right node, which are pointers or references rather to another instances of this AstNode. So what we check here is that if left is not null, so it actually exists, then we print it. If the right node is also not null, we also print it. And every time we go to the next level, we increment the level, so we guarantee that more periods will be printed at the lower level of the tree. So that it's just basically this kind of cryptic output, but it is extremely helpful in debugging of this lexer, so we can observe what really is the result of lexer processing all of the grammar rules. And we say that this print method is a recursive method because it simply calls itself, right? So we call print from main, right here we call print at the level 0, but then as we have to print the entire structure like this or like this, then it calls itself recursively for both left side and right side. All right, so this is fine. We see this type of operation present over here. So now the task is to add our own method that's called evaluate. So the idea is pretty simple idea. I would think it might look like this: public. It will return a double. We'll just do double arithmetic here, and we say evaluate. Doesn't require any parameters, right? So this is the method name evaluate. And here what we get inside the evaluate is that if this is a number, we simply have to convert each node. If you look up over here, each of these nodes from which we construct these trees, they contain the value which is stored as a string. So the node itself does not make any conversions. We have to do this when we evaluate our expressions. Okay, so and there is a left node and the right node, and there's also the type. So the type will be the number in case if the node contains the number. So what we can start with here, we can say that if the type of this node equals the number, right? So we have this constant named number, right? So we can make this comparison. If this is the number, what we need to do is simply return this string, right? This value is stored as a string, so we have to convert it to a double. So what we can do is just use double helper parse, right? Parse double, and of course we will use the value to parse our double. And this is all. We just we deal with the number, so the result of the evaluation of the node that represents the number, all it needs to do is parse double and return the result. The next thing that is proposed over here for our evaluation process, so we can say else, if this is not a number, but if this is something that looks like a minus, right? So we can add this condition here. So if something that looks like a minus, so the type is the minus, we simply use the for punctuation, we use the type as it corresponds to minus, plus, divide, multiply, and all this. And so we say if the type is minus and left node is null, it means that this is a unary minus, and so of course the value has to be coming from the right node, because in case of a unary operator, if you recall earlier, we said that the left node will be null. So what we need to do is we need to return, as it says right here. We can handle this by returning the right node evaluate, which is also the recursive call into the right hand side of our tree, but we will apply this unary minus because that's how it should be evaluated. All right, so let's do something else. Let's say that this is not the case, and so we can continue our else if type of evaluation, and we say, okay, else if this is a minus, then what we need to do here, so this is now, it's a binary minus. So right here we determine that let me see, so this is like this, right? Yeah. And okay, so here we just determined that this is a unary minus, and so the value comes from the right hand side node. But this is then this is a binary minus. So with the binary minus situation, what we need to return is simply evaluation of the left hand side, right? So we take the left node and we evaluate it, this node, and we subtract, because this is binary minus, the right hand side, right? So we just subtract this right node evaluate, and this is it, we're done. So you see how this is quite nice approach, and this is all we need to do to be able to evaluate the actual expression, because the entire structure is in place. We just choose and pick the values from the right side, from the left side, and we do our computations according to how we understand arithmetic operators. And here we apply the actual Java language expressions to do our computations and direct these computations in the right order. So this is all we need to do with this. And so then for a node that represents the binary operator, we just call methods on both sides, which I just demonstrated right here. So for the plus, of course, you use plus. For the minus, like I did over here, we okay, for the minus we call the minus. So this is demonstrated right here, and all we do is just look at the type of the node and we apply proper checks. So also be careful with the division. Let me demonstrate this part. So I would suspect that we continue our evaluation, and somewhere here we might say, okay, if this is a division operator, then of course it's just a kind of copy and paste and replace this minus with the division. So it becomes quite trivial, really. But I would just suggest you to think that maybe if, right, if you, it would be perhaps a good idea to say double left result, right? I'm sorry, double right result, result equals a right node evaluate. So we can basically evaluate the right hand side over here, and then the right result, of course, we can divide by it. But we can say that if, right, we can say if the right result equals 0, and this is a double 0, so we do it like this. What we could do, I mean, we could throw a runtime exception, we could print error message, but we could do something to say handle division by 0. So I'll let you decide what you would like to do with respect of division by 0. This is something that you can handle. If division was 0 was not such as dangerous thing, we just do this and just do something that is very similar to subtraction, to addition, and all of this. But of course, we want to be able to handle division, giving it a little bit more attention. Okay, and so yeah, and I would say that this seems to require some kind of return. So I just return 0.0 at the end, just to be sure, because this is unfinished. This is unfinished if statement, because of course we have more operators to take care of.